first method that we learned for solving a differential equation was direct integration. Recall that if I can isolate the first derivative and it's equal to a function of the independent variable alone, then I can solve this differential equation by integrating both sides with respect to the independent variable. This process only works if the first derivative is isolated and it's equal to a function of the independent variable alone. Today, we're going to look at what happens when we have the dependent variable also over there on the right side of the equation. So section 1.4, we're learning about separable equations and applications. Let's talk about the separation of variables technique. Part A, definition. The first order differential equation, dy over dx equals h of x and y. Now let's pause right here because now we have something different than what we've studied previously. Over here on the right side, we'll have a function of both the independent variable x and the dependent variable y. This differential equation is called separable, provided that h of x and y can be written as a product of a function of x and a function of y. That is, h of x and y equals f of x times g of y. So we'll study all kinds of differential equations that involve both the independent and dependent variables. If we can express that function as a product of a function of the independent variable and the function of the dependent variable, then we call it separable. If it is separable, then we're going to solve it using integration. Before we jump into the method of solution, let's make sure that we can recognize when a differential equation is separable. Example 1, determine if the following differential equations are separable. We have dy over dx equals y squared times x times e to the 3x plus 4y. First of all, observe that our dependent variable is y and our independent variable is x. So we can see over on the right side of that differential equation, we've got a function of both x and y. This equation will be separable provided we can write that right side as a product of a function of x times a function of y. So let's give that a try. Now, notice that we have an exponential function with a sum in the exponent. We can rewrite that as a product of two like bases. Remember, if we have like bases, we add the exponents. So here, I'm just applying that exponential rule in reverse. We're taking the sum of the exponents and rewriting it as a product of like bases. Then, since multiplication is commutative and associative, I can rearrange this into a function of x alone times a function of y alone. Because our derivative is isolated and it's equal to a product of a function of the independent variable and the dependent variable, we say that this is a separable differential equation. So again, how is this different from what we learned last time? Last time we only had a function of the independent variable left over. We could solve it by direct integration. Now we're recognizing we have both a function of x and y, but because we can write it as a product of a function of x and a function of y, it's classified as a separable differential equation. That means it's candidate for the procedure we are about to learn. Let's look at example B. We have dy over dx equals y plus sine of x. Clearly, our dependent variable is the usual y, and our independent variable here is x. On the right side, we have the sum of a function of y and a function of x. We cannot express this as a product. This means this particular differential equation is not separable. That does not mean that it's not solvable. It simply means that we can't solve it by the process that we're going to learn in this section. So let's go ahead and talk about the procedure. Once we recognize that we're dealing with a separable differential equation, what's the procedure for solving it? After separating variables, we will integrate both sides with respect to the independent variable. That is, we're going to integrate both sides with respect to x. Now, that sounds a lot like solving by direct integration, but we're going to have a subtle change as we work out this process. So we're going to move the function of y to the left side by dividing both sides by h of y. So we have 1 over h of y times dy over dx equals g of x. Now we're going to integrate both sides with respect to x. So we'll have 1 over h of y dy over dx. dx. Notice the dx term indicates that I'm integrating with respect to the independent variable x. And we're going to do the same thing on the right side. Integrate g of x with respect to x. Now, because the differential terms behave algebraically, over here on the left side, we can actually cancel out the dx. This is going to leave us with the integral of 1 over h of y dy equals the integral of g of x dx. So once we cancel that dx term, now is where it's going to feel like we're integrating one side with respect to y and the other side with respect to x. Now, to make this a little easier as far as notation purposes go, let's make a little note here. Let's suppose that f of y represents 1 over h of y. Okay, so I can rewrite this side as the integral of f of y dy. This will help us to express that antiderivative in a very simple way. So the integral of f of y dy we can represent as big F of y, and the integral of g of x dx we can represent as capital G of x. And of course, we're going to need our constant of integration. In practice, once again, even though technically we've integrated both sides with respect to the independent variable x, it's going to feel like integrating the left side with respect to y and the right side with respect to x. Now, this is what we call an implicit solution. Implicit because we have a function of y over there on the left side. In some cases, we'll be able to isolate the dependent variable y as a function of x, and in other cases, that will be really inconvenient. So do notice here that we have a function of y, which is implicitly a function of x. So this is what the process looks like in general. Let's apply it to a specific example. On example 2, we'll use the separation of variables technique to find the general solution of the following differential equations. Where possible and convenient, express the solution explicitly. So in example A, we have dy over dx equals y over 1 plus x. First of all, notice this is separable. And we want to collect all the y terms on the left and all of the x terms on the right. So I'm going to do a little shortcut here. I'm going to divide both sides by y to get 1 over y dy, and I'm multiplying both sides by dx. So we get 1 over 1 plus x dx. So once again, that's just algebra, dividing both sides by y and multiplying both sides by dx. We have successfully separated variables. Now we can integrate both sides with respect to the variable indicated by the differential term. So on the left side, the integral of 1 over y dy is the natural log of the absolute value of y. Now, we don't necessarily have to have our arbitrary constant plus c on this side. We're going to have another arbitrary constant on the right side. Ultimately, we could combine those constants into one. So it's only necessary that I have that arbitrary constant on one side. Integrating with respect to x here, we have the natural log of the absolute value of 1 plus x, and now we're ready for our arbitrary constant. Now, for a reason you'll see here in a minute, I'm going to call that constant c sub 1. We have arrived here at our implicit solution. Notice we have a function of y and our goal is to write an explicit solution. That is, we want to isolate y as a function of x. So to isolate y, it's no big deal when we have a natural log function. We can just rewrite it in exponential form. So I'm going to take the argument of the logarithm y equal to e to the natural log of the other side. So I'm just converting from log form to exponential form. So y is isolated, and it's equal to a function of x alone. So this is now an explicit solution. However, we will be able to simplify this a bit and make it a little more readable. Using the same technique that we did on the notes above, I'm going to separate the sum of these exponents as a product of like bases. So each addend in the sum and that exponent becomes an individual exponent on a similar base. Then notice what we have right here. E raised to a constant. Well, since E is a constant and C sub 1 is a constant, A constant raised to a constant produces another constant. So I'm just going to call that constant C sub 2. So we'll say let the second constant, C sub 2, equal C sub 1. Then I could rewrite this as C sub 2 times e to the natural log of the absolute value of 1 plus x. Now, in addition, notice here we have a log property that we could apply. When you raise e to the natural log of something, that causes the exponent, absolute value of 1 plus x, to fall down. Okay? Again, just a property of logarithms and exponential functions. Now we can actually get rid of those absolute value bars by recognizing that what we have inside those absolute values may be either positive or negative when I remove those absolute value bars. So we could call this plus or minus C2 times 1 plus x. Well, if C2 is positive or negative, it is still a constant, and depending on the initial condition, we could get an explicit value for C2. So we're simply going to call that constant, arbitrary constant, C times 1 plus x. So we have allowed constants to evolve over our process of moving to an explicit solution. So when you see something like this, a constant raised to another constant, you can simply replace it with a new constant. Or in the case where you have a positive and negative constant, an initial condition would certainly decide the specific sign for that constant. So we can make it as general as possible, C times 1 plus x. And once again, this is our explicit solution. You learned in the very first section how to check the solution to a differential equation, so you could certainly find the first derivative of this and make sure that it balances the differential equation. If we wanted to move from this general solution to a particular solution, remember we would need an initial condition. Okay, let's try another one of these. X squared times y prime equals 1 minus x squared plus y squared minus x squared y squared. All right, I can tell this one's going to need some algebra. We're not going to be able to solve this by direct integration, the first method that we learned, because if we were to isolate that first derivative y prime, it would not be equal to a function of x alone. So we're going to test out and see if it's separable. Notice there on the right side we've got 4 terms. We can attempt to factor that by grouping. Now I'm going to also rewrite that y prime as dy over dx, because eventually we'll be separating those differential terms. So notice here we've got our first 2 terms, 1 minus x squared. I'm going to group those together in parentheses. And then from the second 2 terms, I'm going to factor out a y squared. That yields the factor 1 minus x squared. So we can factor this by grouping. The 2 terms on the right side now have a 1 minus x squared in common. So I'm going to factor that out, and that leaves behind 1 plus y squared. So notice the right side is a product of the function of x and a function of y, so this is a separable differential equation. So now my goal is to separate the variables. I want everything containing a y on the left, including the differential term, and everything containing an x on the right, including the differential term. Let's see if we can do this all at once. So I'm going to divide both sides by the factor 1 plus y squared, so we're going to get 1 plus y squared on the left, and I'm going to keep the dy term on this side. I'm going to leave the 1 minus x squared factor over here, but we need to divide both sides by x squared and multiply both sides by dx. So we have successfully separated variables. Keep in mind, as you do the algebra to separate variables, it's not logical to have a dy or a dx in a denominator position. So the dy and the dx have to be on the baseline, and that sort of indicates which side you could gather which variable to, okay? Once you have algebraically separated variables, then you're ready to integrate both sides with respect to the appropriate variable. On the left side, you should recognize the antiderivative there is arctangent of y. Now on the right side, we're going to go ahead and split up that rational function. Since we have a monomial denominator, we can divide each term in the numerator by that denominator. So 1 divided by x squared can be rewritten as x to the negative 2, and x squared divided by x squared can be rewritten as 1. That way we can integrate this side term by term. Notice I have lost my integral sign on the left because I've executed that operation, but I still have it over here on the right side because I haven't yet integrated. So when we integrate x to the negative 2, we end up with x to the negative 1 over negative 1. Or if we simplify that as a fraction, we would end up with negative 1 over x. The integral of negative 1 with respect to x is x, and now we are ready for our arbitrary constant. We have actually solved the differential equation, but we still have this solution in implicit form. Notice we have a function of y on the left side, so we have an implicit solution or an implicit form. It's much easier to analyze if you have an explicit solution. So can we solve for y? In this case, it'll be very, very simple. If we take the tangent of both sides, tangent of arctangent, those are inverse functions, so they cancel. And we end up with tangent of negative 1 over x minus x plus c. This is an explicit solution. Explicit simply means y is isolated, the dependent variable is isolated, and it's equal to a function of x alone. It's still a general solution. To go to a particular solution, we would need an initial condition. But I would also like to suggest the fewer the signs that you use in the expression of an equation, the easier it is to read. So what I'm going to do is move this c to the front of my argument and write it c minus 1 over x minus x. Notice we have fewer signs in that equation, and so it makes it just a little bit more readable. As a mathematician, you should always strive to express things in the simplest, most concise, presentable manner possible. So let's do one more example practicing this new technique of separation of variables. In Chapter 1, we're simply looking at different patterns of equations and looking at different processes for solving differential equations. Example 3 says find an implicit particular solution for the differential equation given by e to the 2y minus y cosine of x dy over dx equals e to the y sine of 2x subject to the initial condition y of 0 equals 1. Now, I'm not going to attempt to solve this by direct integration, the first process that we used, because we can see we've got the independent variable x and the dependent variable y mixed up together in this equation. So the next thing that I'm going to try is simply to separate the variables. I want to collect all the terms containing a y on the left side and all the terms containing an x on the right side. And that just requires some algebra. So I'm going to keep this factor, e to the 2y minus y on the left side, and I'm going to divide both sides by e to the y. That's going to move that factor over here to this side. We'll keep the dy in the numerator on the left. Now, working over here on the right, we still have a sine of 2x on this side. We can divide both sides by cosine of x to bring our variables over here, and we can multiply both sides by dx. So we have successfully separated our variables. This means that we can solve the differential equation by integrating the left side with respect to y and the right side with respect to x. Before we integrate, we do need to prep our integrand for an easy process. So on the left side, we can divide both terms of the numerator by the denominator. E to the 2y divided by e to the y gives us e to the y. I'm just subtracting the exponents there. And then for our second term, y divided by e to the y, I'm going to rewrite it y e to the negative y because that makes me think of integration by parts. Over here on the right side, we can replace sine of 2x with the double angle identity, 2 sine of x times cosine of x. And we have a cosine of x here in the denominator that we'll be able to cancel. And that's going to simplify our integration process. So working on the integral on the left side, we can integrate term by term. The integral of e to the y is e to the y. But to work on that second term, negative y e to the negative y, we're going to need to use integration by parts. So to indicate this, I'm just going to postpone that integration here to the next step. Let's go ahead and knock out this integral over here on the right side. The integral of 2 sine of x, the integral, of course, our constant filters through to the antiderivative. The integral of sine of x is negative cosine of x, and we'll introduce our arbitrary constant. So back to our pending integral over here on the left, we can use integration by parts. Let's suppose that u is y, du then is dy, dv is our exponential e to the negative y dy. Integrating, working our way up here, we'd end up with e to the negative y over negative y, or we could write that negative e to the negative y. So I'm going to drop down my term. I've already integrated e to the y. We're going to have to be careful with this negative right here. As we apply the integration by parts formula, we definitely want to correctly distribute that negative. Integration by parts formula is u times v. That's going to give me negative y e to the negative y minus the integral of v du. Notice that v is negative e to the negative y, so that's going to cancel this negative here, and du is dy. And then we'll just drop down everything else that we've executed so far. To finish up our last integral here inside parentheses and taking care of distributing this negative, we have e to the y plus y e to the negative y. Now notice here, I'm going to distribute this negative to get a negative here, just distributing here. And when we integrate e to the negative y, we're going to get negative e to the negative y. So that's going to cancel that negative sign there. And this equals what we have over here on the right side, negative 2 cosine of x plus c. So this is our implicit solution to the differential equation. Implicit because it is an equation containing both x and y. Y is not isolated as a function of x, but the derivative term is gone, right? So we have solved the differential equation. We're just dealing with an implicit solution. Notice in this case, it would be extremely difficult, if not impossible, to solve this equation for y. So we're going to leave it implicit. However, we do want to go from an implicit solution to a particular solution. Remember, to obtain a particular solution, we apply our initial condition. Our given initial condition is y of 0 equals 1. So we're going to plug 0 in for x and 1 in for y. So looking at our implicit solution, we have e to the y. Remember, we're replacing y with 1, plus 1 times e to the negative 1 plus e to the negative 1, replacing y with 1. On the right side, replacing x with 0, we have 2 cosine of 0 plus c. Now, this is going to give us enough information to solve for c. Simplifying over here on the left side, we have e plus, when we combine like terms, we have 2e to the negative 1. Recall that cosine of 0 is equal to 1, so we have negative 2 times 1 plus c. So to solve for c, we can add 2 to both sides. And I'm going to rewrite that 2e to the negative 1 is 2 over e and plus 2. So there is our constant, which will translate our implicit solution, which is general, to an implicit particular solution. So let's update our solution and make it a particular solution. We're going to end up with e to the y plus y e to the negative y plus e to the negative y equals negative 2 cosine of x plus c. And we obtained e plus 2 over e plus 2 for our constant. That is an implicit particular solution. Now, if you were able to follow that process and you're comfortable with the calculus, then that is the new information for this section. That's the new method. So at this point, you know 2 methods for solving a differential equation: direct integration and separation of variables. Make sure you can recognize when to use each of those methods. Now, the remainder of this section is devoted to looking at applications. Applications where we model a specific situation with a differential equation, and it happens that the differential equations that we're going to use for our models can be solved by separation of variables. Part 2, natural growth and decay. The differential equation, or the model that we are about to study, is very standard, and it applies to a myriad of different applications. natural growth and decay. Any quantity whose time rate of change is proportional to its current size can be modeled by the differential equation dx over dt equals kx. So I've got a time rate of change on the left, right? The rate of change of x with respect to time t, and it is proportional to, notice the constant in proportionality k, its current size, modeled by the dependent variable x. This prototype differential equation can be used to model such quantities as population, continuous interest, radioactive decay, and even drug concentrations in the bloodstream. So this is a very universal and useful model. This equation is readily solved by separating variables. So let's go through that process. Again, do notice that our dependent variable this time is x. That takes some getting used to because oftentimes we use x as the independent variable. Our independent variable here is time. So the solution, or t, the solution to this differential equation is x as a function of t. So we're looking for x of t. So notice over here, we do not have the independent variable. That is the dependent variable. The reason I'm pointing that out is because you may be tempted to solve this by direct integration. Let's just integrate both sides with respect to the independent variable. But we have the dependent variable over there on the right side. That means we need to solve it by separation of variables. So we're going to collect all of the x's on the left. That is, we're going to divide both sides by x, and we're going to leave our differential term dx here. And then we want everything involving the independent variable t on the right. Now, I'm going to leave this constant in proportionality on the right and multiply both sides by dt. Then we can solve by integrating both sides, the left with respect to dependent variable x, the right with respect to independent variable t. And remember, k is a constant. The integral of 1 over x dx is the natural log of the absolute value of x. And on the right side, integrating with respect to variable t, we end up with kt, and let's go ahead and add an arbitrary constant. As we saw previously, we can isolate x. And this time I'm going to show you in a little more detail what to do with the absolute values. Okay, I'm going to raise the right side, or take e and raise it to the kt plus c. And what we can do with those absolute values is recognize if we remove them, that's going to cause a positive or a negative result. As we saw before, we can rewrite this exponential as the product of like bases. And then notice right here we have a constant e raised to a constant. Well, that's another constant. That makes a new constant. I'm not subscripting the constants this time, just to show you what the practice feels like as you solve these differential equations. Then notice we have positive and negative constant c. That's an arbitrary constant. We can simplify that by simply writing it x equals ce to the kt. An initial condition would indicate the proper sign of that coefficient c. So when you have this very simple differential equation where the time rate of change is proportional to the current size of the population or investment or whatever it is that you happen to be modeling, then this is the automatic solution. So as you work the application problems in your homework and also on these notes, you don't necessarily have to solve the differential equation over and over and over. You're always going to get the same pattern of solution. So if you see this differential equation and recognize it, then you can automatically assume that the solution takes this form. Let's look at some specific applications using this model. We'll start with radioactive decay. If capital N of T represents the number of atoms of a certain radioactive isotope at time t, okay, so we're going to measure the number of atoms in a radioactive isotope at time t. If we have a radioactive isotope, then the number of atoms should be decreasing, right? Because the atoms dissolve into their subatomic particles and the amount of the substance that you have actually decreases. The decay rate will be constant k. Then it can be viewed as a decreasing population model. That is, the rate of change of the number of atoms in with respect to time is equal to negative kn. Notice that this derivative is negative, which indicates that the number of atoms is in fact decreasing. Note, the decay rate for a certain element is often expressed in terms of its half-life. You've probably heard of half-life in biology classes and chemistry classes. We're going to call it tau. That's the Greek letter tau, and it's calculated as natural log of 2 divided by k. But we want to verify this based on what we know about this differential equation. So notice the differential equation that we're using here has exactly the same pattern as the one we studied in general. The only difference is our dependent variable is now named n instead of x. So if we went through the process of separation of variables, we could say the solution n of t is going to look like some constant. We called it c above. I'm going to call it n sub 0, n naught. That's going to be the initial amount of our population times negative kt. So again, if we come right back up here to our notes, we're just recognizing that the pattern of the differential equation matches this. So this is the pattern of the solution. Again, the dependent variable we're considering here is not x, it is capital N. Also observe that k is negative in this particular differential equation, and instead of using arbitrary constant c, I'm making it more specific and calling it n sub 0. Anytime you see a subscripted variable, assume that it represents a constant. So in fact, it's going to represent the initial population. So our goal is to verify that the half-life for this model is calculated as natural log of 2 divided by the decay rate k. So let's express this as an initial condition. So our initial condition we could write as n of the half-life. Remember, we decided to call that tau. N of tau is going to be exactly half of the original amount of the element that I started with. Okay, now remember, a half-life is a length of time. It is the amount of time that it takes for the substance to decay to exactly half of the original amount. If my original amount is n naught, then half of that would be n naught over 2, and that's going to take an amount of time represented by tau. We're attempting to prove that tau equals natural log of 2 divided by k. So if we plug this information into our given solution, we're going to replace n of t with the value n naught over 2, and we're going to replace the variable t with our constant tau. Now my goal is to solve for tau. So let's go ahead and divide both sides by n naught. When we do that, it cancels from both sides, and we have e to the negative k times tau. We can solve this by taking the natural log of both sides, or you can just convert directly to natural log form. I'll take you through the steps this time. If we have natural log of something raised to a power, remember properties of logarithms say that we can move that power down to the left. So we have natural log of 1/2 equals negative k tau natural log of e. Recall that natural log of e is equal to 1. So here we have negative k tau times 1. If we solve for tau, we're going to end up with natural log of 1/2 divided by negative k. Now remember, keep your eye on the goal here. We're attempting to prove that we get natural log of 2 over k. We're not quite there. What we can do is manipulate this logarithm. Let's rewrite 1/2 as 2 to the negative first power, and using that same property of logarithms we did a moment ago, we're going to move that exponent down in front as a coefficient. So we have negative 1 times natural log of 2 divided by negative k equals tau. Then you can see that the negatives cancel, and we can say therefore, those 3 little dots mean therefore, tau is in fact natural log of 2 divided by k. So we did not actually solve that differential equation. We simply recognized that the pattern of this differential equation matches the general pattern that we studied above, and so we made an assumption that the solution is going to look the same way. It's going to follow the same pattern. Then we took the idea that the half-life, which decays the original amount of your substance to exactly half of the original amount, we determined this initial condition, right? N of tau equals n naught over 2. We plugged that in in order to solve for tau. So we took that information, we plugged it into our solution, we worked through the algebra, and we were able to solve for the half-life. So if we have a radioactive decay differential equation, which looks like this, with corresponding solution like so, then the half-life is always going to be calculated as natural log of 2 divided by the decay rate for that specific element. It's quite possible that you'll see something very similar to that in a chemistry or a physics lab. Let's stick with this idea of radioactive decay and look how this might apply to carbon dating. This is example 4. It's taken from page 43 of your text, problem number 36. It says, carbon taken from a purported relic of the time of Christ contained 4.6 times 10 to the 10th atoms of carbon-14 per gram. Carbon extracted from a present-day specimen of the same substance contained 5.0 times 10 to the 10th atoms of carbon-14 per gram. Compute the approximate age of the relic. If we can find the age of the relic, then we can make a decision about its authenticity. Remember, this is claimed to be a relic from the time of Christ. Now, if you're interested in more information about how carbon dating works, it's summarized on page 37 to 38 in your textbook. Ultimately, organic living things take up carbon-14 as they breathe and live and move around. When something dies, it ceases to take up carbon-14. Okay, so when someone is living, when you have a living thing, the amount of carbon-14 in their body is going to reflect the amount of carbon-14 in the atmosphere and in the environment around them. When something dies and it ceases to take up carbon-14, the carbon-14 in their bodies begins to decay radioactively. So by looking at how much carbon-14 is from some sort of relic, you can determine the age of that relic based on the amount of carbon-14 in the atmosphere over time. So what we're going to do is construct a model that follows the differential equation, the same pattern of the differential equation that we've been studying, which will have a solution, n of t, n naught e to the negative kt. Okay, so I'm jumping straight to the solution to the differential equation. K, of course, is the decay rate, and we are supplied the decay rate here for carbon-14. So we'll be able to go ahead and plug that in for K. So what we want to do is update our model to match the specifics of this problem. Remember, N naught is the initial amount that a substance contains. In this case, this substance had 4.6 times 10 to the 10th atoms of carbon-14 as its original value. And let's go ahead and replace K with 0.0001216. 1, 2, 3 zeros there. Now, the present day specimen contains 5.0 times 10 to the 10th atoms. Whoops, forgot my T. Let's go ahead and write our T there. So the present day specimen, the amount or the number of atoms here, we're going to plug that in for N of T, is 5.0 times 10 to the 10th. So this is going to set up an equation that I'll be able to solve for T. T is going to be time in years. So this is simply going to require some algebra. Let's divide both sides by 10 to the 10th. When we divide by 10 to the 10th, that's going to cancel. Then we can divide both sides by 4.6. And to avoid rounding error here, I'm just going to leave it as 5 divided by 4.6 equals e to the negative 0.0001216 t. Oops, I keep losing my t. Don't lose your t. Let's take the natural log of both sides, or you can just think I'm converting this into natural log form. So we'll do it a little shorter this time than we did on the previous example. Natural log of 5 divided by 4.6 yields the exponent, 0.0001216 t. So to solve for t, I can divide both sides by that constant. So our time is natural log of 5 divided by 4.6 divided by negative 0.0001216. And that's time in years. Now, if we type that into our calculator, and we can approximate here on the very last step, we'll obtain negative 685.70. And again, this is time in years. So the negative simply means that we're measuring back in time. How old is this relic? If our present time is time 0, then we're talking about approximately 686 years ago. So this relic is claimed to be from the time of Christ, which was approximately 3 BC to 30 AD, around 2,000 years ago, 2,000 plus years ago. So we can say our conclusion is the relic is not authentic because the time of Christ was between 3 BC and 30 AD, approximately, depending on which chronology you follow, okay? Again, that is around 2,000 years ago, give or take a few years, but it is certainly not matching up to the 685 years ago. So the relic is not authentic. So that's kind of an interesting problem. We took an exponential function, which is the result of a solution of a differential equation using separation of variables, and we were able to date a relic and make a conclusion as to its authenticity. That's when your mathematics becomes very real and very useful. Let's look at another application of the same differential equation in a different situation. This one has to do with drug elimination. The amount A of T of a certain drug in the bloodstream, measured by the excess over the natural level of the drug, will decline at a rate proportional to the current excess amount. That is, the rate of change of A, the amount of the drug, with respect to time t, is equal to negative lambda times A. So lambda in this case is the rate of decay. Notice this says lambda is greater than 0. That's the elimination constant of the drug. It's like the decay constant for our carbon-14. But instead of looking at a radioactive element, we're looking at the metabolism of medicine in the bloodstream. But the laws, the rules governing those things are the same. Another way to think about this is dA over dt equals lambda A, where lambda is less than 0. So we're just ensuring, either way you look at it, that that coefficient is negative. So the amount of drug in the bloodstream is decreasing when you have a negative coefficient. So this is the exact same differential equation that we studied in general. It can be solved by separation of variables, and we can make an assumption then about the nature of its solution. Let's look at example 5. It says, suppose that sodium pentobarbital, I spelled it wrong, I need an extra T in there, pentobarbital is used to anesthetize a dog. So here we're looking at veterinary medicine. The dog is anesthetized when its bloodstream contains at least 45 milligrams of sodium pentobarbital per kilogram of the dog's body weight. So anesthetized, sleeping, right, so you can operate on the dog when you have 45 milligrams of the medicine per kilogram of the dog's body weight. Suppose also that sodium pentobarbital is eliminated exponentially from the dog's bloodstream. That is, this is the differential equation that it obeys, and the solution to that differential equation is exponential. The half-life is 5 hours. What single dose should be administered in order to anesthetize a 50-kilogram dog for 1 hour? So this is a really important question, right? Guys, we're talking about Fido here. Fido is depending on your ability to correctly analyze the math here so that he will stay anesthetized during surgery for an hour, right? You don't want him waking up during surgery. So looking at our model, we can make an assumption about the solution, or we could certainly solve it by separation of variables. We'd end up with A of t equals an initial amount, A naught, e to the lambda t. Okay, this is the same solution that we've been looking at over and over again. We're just changing the details. So instead of dependent variable x or n, our dependent variable now is A. Our independent variable is t. Lambda is the rate of decay, and A naught is the initial amount of the medicine in the bloodstream. In order to make a good conclusion about this question, we're going to need to know the decay rate lambda. We need to find lambda. So let's use the clue about the half-life. The half-life is given to be 5 hours. So if our initial amount is A naught and the half-life is 5 hours, then after that 5 hours, we would end up with exactly half of the original amount. Notice when I divide both sides by A naught, that this half-life is independent of that initial amount A naught. It just cancels. When we solve for lambda, we have natural log of 1/2 equals, I'm going to rewrite that as 5 times lambda. So lambda is equal to natural log of 1/2 divided by 5, okay? Or as you're going to see here in a minute, we're going to stack up the exponents. It might be easier to view this as 1/5 times natural log of 1/2. So this is the decay rate for this particular medicine, sodium pentobarbital. So let's use this lambda value and we're going to go back and update our general solution. We'll make it a little more specific. So our model A of t is initial amount A naught times e to the lambda. We're going to plug in 1/5 times natural log of 1/2. That's the coefficient of t. Now, we certainly could stand to simplify this. That will help us in our analysis. So what I'm going to recognize here is that on the natural log function, I actually have two coefficients. I have 1/5 and t, right? Neither of those belong to the argument. That's a coefficient. So what we can do is move the coefficient of the natural log up into the exponent position. So we have A naught e to the natural log of 1/2 raised to the t over 5. Okay, so I've got lots of exponents stacked up there. But remember, whenever you take the base e and raise it to a natural log base e, those are inverse functions and they cancel, and the argument falls out. So we have 1/2 times t over 5. So this is our more specific general exponential model for this particular medication. Now that we have a specific model, let's go back and revisit the question and see what we can do about it. It says, what single dose would be administered in order to anesthetize a 50-kilogram dog for 1 hour? What single dose? So what initial amount should we give this dog so that he remains anesthetized for 1 hour? Okay, so this is essentially leading us to an initial condition. So we want our initial condition to be A of 1 equals, so after 1 hour, okay, after, not at the beginning of the hour, after 1 hour, the dog must be anesthetized. He's going to be anesthetized if he has 45 milligrams of sodium pentobarbital per kilogram of his body. Remember, we're dealing with a 50-kilogram dog here, so 45 times 50, or if you put that into your calculator, you're going to get 2550. Which means after 1 hour, there would still be enough medication in this dog's bloodstream to have him anesthetized. So let's plug this in. We're going to plug 2550 in for A of t, and we're going to plug 1 in for t. So we have 1/2 raised to the 1/5. So the initial amount of medicine that we need to administer to our dog here is 2550 divided by 1/2 raised to the 1/5 power. So I paused here to type this into my calculator. I realized I have just a little bit of an error here. 45 times 50 is 2250. Fido's dependent on me, y'all. I don't want to let him down, so I'm going to correct that. Okay, 2250 divided by 1/2 to the 1/5 power. Then when we approximate that, we're going to get 2585 milligrams of medication. So if you were working along with your calculator, you probably caught that. So 2585 milligrams of medication. So that's how much we would administer at first. Then we can be sure that after an hour, he is still anesthetized for the medical procedure. So really what we're doing here is analyzing an exponential function, not a whole lot of calculus or differential equations. We're just recognizing that that particular exponential function comes from the solution to a very simple differential equation that can be solved by separation of variables. So as we go through these problems, don't be overwhelmed by the details. Once you finish those problems, I want you to look back over them and look at how they're similar. Look at the big structure, the overall pattern. You've got the same differential equation, the same solution to the differential equation. The only thing that's changing each time is how we name those dependent variables, independent variables, and parameters. Then the details of the problem, we're using that to establish initial conditions and make conclusions about those situations. Now, one more problem that I want us to examine that involves separation of variables is called Newton's law of cooling. You've probably seen this in a science class, and if you haven't yet, you may see it in a future physics class. So you'll have the math ready to go to understand that concept. The time rate of change of the temperature, capital T of little t, of a body immersed in a medium of constant temperature, A, is proportional to the difference A minus T. Okay, pause right there for a minute. We have capital T. Capital T represents temperature. Little t, the independent variable, represents time. Wouldn't hurt to write that down. So big T is temperature. Little t, independent variable, is time. They are not the same. So we're going to take some sort of object. Let's say that you are taking a cake out of the oven, right? The cake out of the oven, you're taking it out of the oven, you're going to place it at room temperature. So you're going to immerse this cake in room temperature. Now, what's going to happen to the temperature of that cake? Well, the temperature of the cake is going to decrease until it eventually matches the temperature of the surrounding medium. So that change in the temperature of the cake is modeled by what we call Newton's law of cooling. So the rate of change of the temperature, capital T, with respect to time, little t, is proportional to, so K is our constant of proportionality, the difference between A, the temperature of the surrounding medium, minus capital T, the changing temperature of the object in question. And again, K is a positive constant. So observe here that capital T over here is the dependent variable, not the independent variable. So I cannot solve this by direct integration. We'll have to solve it by separation of variables. Okay, let's look at one example regarding forensic science. Just before midday, the body of an apparent homicide victim is found in a room that is kept at a constant temperature of 70 degrees Fahrenheit. Okay, so the surrounding medium is at a temperature of 70 degrees. I'm going to make a note of that. At 12 noon, the temperature of the body is 80 degrees Fahrenheit, and at 1 p.m. it is 75 degrees Fahrenheit. Okay, normal temperature is 98.6, something like that. So this is going from temperature 80 to 75 in 1 hour. So we can see the temperature is decreasing. Assume that the temperature of the body at the time of death was 98 degrees and that it has cooled in accord with Newton's law. What was the time of death? Okay, so let's write our differential equation. We have d capital T divided by dt equals K times A. We know that part is 70 minus capital T. This particular differential equation does not match the pattern of differential equations we've been studying. This one is a little bit different. So we do need to go ahead and solve this one by separation of variables. So we want everything involving a capital T over on the left side. So I'm going to divide both sides by 70 minus capital T, and I'm going to leave my d big T on the left side. And then we can multiply both sides by d little t. Then I can integrate both sides with respect to the appropriate variable. Integrating on the left side, notice there we have, if we let u be 70 minus t, du would be negative dt. So when we integrate, we're going to get negative natural log of 70 minus capital T. And on the right side, KT plus C. Let's divide both sides by that -1. We're going to get negative KT minus C. Isolating the argument 70 minus T, or rewriting this in exponential form, we have negative KT minus C. Or, as we've done before, we could express that e to the negative KT times e to the negative C. Notice we have constant to a constant here, so we can rewrite that. We'll just call it a new constant C times e to the negative KT. Let's go ahead and isolate T. We'd end up with T equals 70 minus CE to the negative KT. And don't forget, capital T is a function of little t. So this is the general solution to Newton's law of cooling for this particular room temperature. I'm going to label this as the general solution. To make it particular, we're going to need to glean our initial conditions. So let's go back and revisit the information in the problem. At 12 noon, okay, we're going to call this time 0. So at 12 noon, or time 0, we can say the temperature of the body was 80 degrees Fahrenheit. At time 0, so our initial check, we're going to assume that's 12 noon, the temperature was 80 degrees Fahrenheit. So let's go ahead and plug this into our general solution and see if we can find one of our parameters. Notice we have parameter C and parameter K. So using our general solution, I'm going to plug 80 in for capital T of T, and I'm going to replace little t with 0. We know that e to the 0th power is equal to 1. So we can solve for C here. Looks like C is -10. So I'm going to go back to my general solution and update it. I'm going to replace the C with -10. So notice we have minus negative C. That's going to become plus 10e to the negative kt. So we have a little bit more information. It's not yet a particular solution because we don't know K, but we do have another condition, right? Our scientists here took another temperature at 1 p.m. Okay, this is 1 hour later, so after 1 hour, the temperature is 75 degrees. So I'm going to use this to figure out K. So we can plug 75 in for the temperature, and we can plug 1 in for T. K times 1, and then we can solve for K. So subtract 70 from both sides. Divide both sides by 10. Rewrite in logarithmic form. Natural log of 1/2 would be negative K. If you divide both sides by -1, K would be negative natural log of 1/2. Or if you move that coefficient up into the exponent position, we could call that natural log of 2 for K. So let's go back once again and revisit our solution. Let's use this one right here and update it. We're going to replace K with natural log of 2. So our particular solution then would be 70 plus 10 times e to the negative natural log of 2 times t. Now, before we start answering the question, let's simplify this expression right here. Notice that the natural log of 2 has a coefficient of -1 and t, so we could rewrite this as natural log of 2 raised to the -t. Applying our rules of logarithms, we could simply call that 2 to the -t. So this is our particular solution. The power of this particular solution is that it is predictive. We can determine the temperature of the object at any time t. So this is our particular solution. Okay, so back to the question. It says, what was the time of death? So we're assuming that the temperature of the body at the time of death was 98 degrees, but the time is unknown. So we're trying to figure out at what time was the temperature 98 degrees. So I'm going to replace T of T with 98 degrees, and I'm simply going to solve this equation for T. Okay, So working out our algebra here, we're going to subtract 70 from both sides. Divide both sides by 10. Take the natural log of both sides. I'm going to move the exponent down in front as a coefficient. And then divide both sides by negative natural log of 2. So you have natural log of 2.8 divided by negative natural log of 2 to get our time. Okay, so plug that into your calculator and you're going to find out t is approximately negative 1.5. Negative time means before our initial time, right? Remember we said the initial time, the time that we took the first measurement, the initial time is 12 noon. So we need to figure out an hour and a half, this is 1.5 hours, before noon. An hour and a half before noon is 10:30 a.m. So our conclusion is that the time of death was 10:30 a.m. Okay, and that comes from two separate measurements of temperature and understanding that this is following Newton's law of cooling. So in this section, the new process that you learned was separation of variables. Make sure you can solve a differential equation by separation of variables. And then we looked at exponential growth and decay with a specific differential equation we could solve with separation of variables and several examples of that, and then also Newton's law of cooling. So you are ready to begin your homework for this section. Thanks for listening.